question says a small piece of cesium metal phi equals to 1.9 electron volts is kept at a distance of 20 centimeters from a large metal plate having a charge density of 1 into 10 to the power minus 9 coulomb per meter square on the surface facing the cesium piece. A monochromatic light of wavelength 400 nanometers is incident on the cesium piece. Find the minimum and the maximum kinetic energy of the photoelectrons reaching the large metal plate. Neglect any charge in electric field. It's by the change in the electric field due to the small piece of cesium present. So we are having a large plate and a cesium metal. And all we need to find is the potential difference between these 2 points, because in case we are able to find the potential difference, we will be adding the corresponding energies EV to the minimum and the maximum kinetic energies of the photoelectrons that are getting emitted, as we did in the previous problems. So here we can write down the energy density that is given in the question, 10 to the power minus 9 coulomb per meter square. The work function being given 1.9 electron volts. The distance being 0.2, that is the distance between the two plates D. And the lambda being 400 nanometers. Right? So here we know that we need to find the potential difference. And we know that the potential difference is basically the electric field into the distance between the plates, that is D. And why we are writing it like this is because electric field is uniform. There is no change due to the cesium present over there. And there is a large plate, so electric field is constant. So we can do it like this. So our task reduces to find the electric field. And we know that electric field due to a large plate is sigma by epsilon naught. So basically the voltage between the two plates is sigma by epsilon naught into D. Finding the value of this potential, we get sigma, that is 1 into 10 to the power minus 9 into the distance, that is 0.2, and epsilon naught, which is 8.85 into 10 to the power minus 12, giving us a value of approximately 22.6 volts. So this is the difference of 22.6. Now, whatever kinetic energy with which the electrons are emitted, this much of energy will be added to them. So we can simply find the minimum and the maximum kinetic energies of the photoelectrons reaching the larger plate. So let us find that particular kinetic energy, the limiting kinetic energy actually. We know that the energy of the photon, that is the light incident, is h nu, which is also equals to the work function plus the kinetic energy. So the kinetic energy is basically the energy of that photon minus the work function. So I can write it as 4.14 into 10 to the power minus 15 into 3 into 10 to the power 8 over 4 into 10 to the power 7 minus 1.9, giving us a value of 1.205 electron volts. So we can say that the photoelectrons emitted can have any random kinetic energy between 0 to 1.205, right? Now, if they have the zero kinetic energy, they will be having, on reaching the larger plate, the kinetic energy as per this voltage. And if they are having 1.205, then this much will be added to that. So all we can say is the minimum kinetic energy will be the minimum when they are emitted plus due to the voltage. So that comes out to be 22.6 electron volts. And the maximum kinetic energy will be corresponding to the maximum kinetic energy when they are emitted, which is this, plus due to the voltage, this is this, giving us the value of 23.8005 electron volts. So these minimum and maximum are governed by the minimum and maximum while they are emitted, because the change in energy due to the potential is same.